The Atlantic Ocean, March 1943. Lieutenant Commander Peter Dönitz peered through the periscope of U-boat 621, the faint glow of instrument lights painting his face in ghostly blue. The sea above was calm, deceptively so. Somewhere beyond the grey horizon, he knew, another Allied convoy was steaming toward Britain, a string of merchant ships carrying food, oil, and weapons vital for the island's survival. For nearly 4 years, men like Dönitz had been the predators of this vast and lonely ocean. The Atlantic had been their hunting ground, and the world had watched in terror as German U-boats nearly succeeded in cutting Britain's lifeline. Between 1939 and 1942, the Kriegsmarine's U-boat arm waged a campaign of such devastating success that Winston Churchill would later admit, "The only thing that ever really frightened me during the war was the U-boat peril. Thousands of merchantmen had been sunk, millions of tons of supplies sent to the bottom. Entire convoys vanished, and British ports struggled to stay open under the strain. The submarines struck with cold precision, surfacing under cover of night, launching torpedoes at silhouetted ships, and then slipping beneath the waves before the escorts could react. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you." Yet now, as Dönitz peered through the lens, something felt different. The balance had shifted. Reports from other U-boats spoke of aircraft appearing out of nowhere, of bombers dropping depth charges in the middle of the night, of submarines spotted on the surface even when visibility was near zero. Some captains swore Allied planes were finding them in complete darkness, an impossibility, according to every bit of training and experience they possessed. The hunters, it seemed, were becoming the hunted. What none of them fully understood was that the Allies had discovered a way to see through the night, and even through fog, not with light, but with invisible waves of energy. It was called centimetric radar, and it would change the course of the Battle of the Atlantic. Early in the war, radar was already a known quantity. The British had deployed their famous chain-home radar stations along the coast to detect approaching bombers, and Allied ships carried surface search radars that could pick up large targets. But those early systems worked on long wavelengths around 1.5 meters, and their resolution was poor. They could detect a convoy, but not distinguish an individual ship. Worse, they couldn't spot something as small as a submarine periscope or conning tower, especially amid the clutter of waves. When a U-boat surfaced at night to recharge its batteries, it became invisible to both radar and human eyes. The darkness was its armor. The only thing that betrayed its presence was the faint phosphorescent wake behind it, something no radar could detect. This night blindness plagued Allied anti-submarine efforts. Escort ships relied on visual sightings or the crude sonar ping of ASDIC, which was useless once a submarine surfaced. Aircraft could only attack during daylight. As a result, U-boats ruled the night until a handful of scientists at the British Admiralty and the Telecommunications Research Establishment, TRE, began experimenting with something radically different. The breakthrough began with a theoretical problem. Long-wave radar couldn't detect small objects, so why not shorten the wavelength? In 1939, British physicists John Randall and Harry Boot developed the cavity magnetron, a device that could generate microwave radiation at wavelengths measured in centimeters rather than meters. This promised a radar beam so narrow and precise it could detect something as small as a periscope protruding from the sea. But the idea was initially dismissed. Many military officials argued that such short wavelengths would scatter or be absorbed by rain and sea spray. The equipment seemed delicate, untested, and incompatible with existing aircraft or ships. Resources were already stretched thin, and radar engineers were told to focus on improving proven systems. It took the pressure of war and Britain's near starvation by 1941 to change minds. Convoy losses reached catastrophic levels, and Churchill demanded answers. When the magnetron was finally demonstrated, its potential became undeniable. A tiny bomber flying above the English countryside could pick out a single car moving along a dark road. If it could do that, engineers realized, it could find a submarine. By 1942, British scientists had miniaturized the magnetron enough to fit inside aircraft. The air-to-surface vessel, ASV Mark III radar, was born the first operational centimetric radar. It was soon installed on long-range patrol planes like the consolidated B-24 Liberator and the short Sunderland flying boat. These aircraft could now patrol vast stretches of the Atlantic, guided by radar that could spot a submarine periscope from miles away, even on the darkest night. To the U-boat crews, it was witchcraft. A plane could appear without warning, its radar invisible to any detector they had. The first sign of danger was often the roar of engines overhead or the splash of depth charges in the water. The Germans scrambled to understand what was happening. They had their own radar detectors, devices like the Metox, which could pick up the longer radar wavelengths used by earlier Allied systems. But Metox was useless against centimetric radar, whose frequency was far beyond its range. U-boat captains, trusting their instruments, often surfaced thinking the skies were clear only to be ambushed moments later. As the Allies refined the technology, the results were dramatic. In the spring of 1943, the Battle of the Atlantic reached its climax. That March, Dönitz's U-boat command sent over 100 submarines into the North Atlantic in coordinated Wolfpack attacks. They expected a slaughter of Allied shipping. Instead, it was the U-boats that were slaughtered. Aircraft equipped with the new radar, working with escort carriers and destroyers, sank U-boats at a rate never before seen. Between March and May 1943, more than 40 German submarines were destroyed. For the first time, Allied convoys crossed the ocean with minimal losses. The effect on morale was devastating. Veteran U-boat commanders began to question their survival chances. Dönitz himself, now admiral of the U-boat fleet, admitted that the new Allied detection methods had rendered the Atlantic no longer a hunting ground but a graveyard. The Germans rushed to develop countermeasures, including the Naxos radar detector, which could sense centimetric emissions, and snorkels that allowed U-boats to remain submerged while running their diesel engines. But by the time these innovations appeared, the tide had turned irreversibly. Behind the scenes, the victory was as much scientific as it was military. The engineers and scientists who fought for centimetric radar had done so in the face of bureaucratic resistance, technical hurdles, and skepticism from the highest levels of command. They had been told the idea was impractical, that it violated known physics, that the components would never survive the vibration and moisture of combat aircraft. But necessity has a way of silencing doubt. The desperate situation in the Atlantic forced the military to listen to the innovators. Laboratories that once struggled for funding suddenly became national priorities. American and British scientists collaborated through the Tizard mission, sharing the magnetron design across the Atlantic. The U.S. then mass-produced the technology on an industrial scale, fitting it into aircraft, ships, and even small coastal patrol craft. The result was one of the most decisive scientific victories of the war, a triumph not just of invention, but of persistence. By late 1943, the U-boat threat had been broken. The once invincible wolf packs were hunted relentlessly, forced to operate in shallower waters or retreat entirely. Convoy losses plummeted, Allied supplies flowed freely, and the path to D-Day opened. In the end, centimetric radar was more than a new weapon. It was a new way of seeing. It proved that the difference between victory and defeat could hinge not on sheer firepower, but on the courage of those willing to challenge assumptions. As Lieutenant Commander Peter Dönitz finally lowered his periscope that cold March night, the Atlantic stretched before him as it always had, vast, indifferent, eternal. Yet unseen in the darkness above, a Liberator was already circling, guided by a silent radar beam that pierced the Black Sea and found its mark. The era of the U-boat hunter was ending. The age of radar had begun. In 1935, the concept of using radio waves to detect objects seemed promising in theory, but plagued by practical limitations. The British had developed radio direction finding systems that could locate the direction of radio transmissions, but using radio waves to detect silent objects like ships or aircraft required solving problems that many engineers considered insurmountable. The wavelengths that could penetrate fog and darkness were too long to reflect off small objects. The wavelengths short enough to detect aircraft or submarines required power levels that existing transmitters couldn't generate. Robert Watson Watt and his team at the Radio Research Station in Slough, England, tackled these problems with the kind of obsessive determination that characterizes breakthrough innovation. They needed to generate short wavelength radio pulses with enough power to travel miles, reflect off metal objects, and return to a receiver with sufficient strength to be detected. The technical challenges were formidable. Generating high-power radio waves at short wavelengths required vacuum tubes that didn't exist. Detecting the faint returning echoes required receivers sensitive enough to amplify signals 1,000,000 times without amplifying background noise to the point of uselessness. By 1940, British engineers had developed Chain Home, a network of radar stations that provided early warning of German bomber attacks during the Battle of Britain. These massive installations, with antenna towers reaching 350 feet into the air, could detect aircraft at ranges exceeding 100 miles. They were technological marvels that helped save Britain from invasion, but they had severe limitations. The systems were enormous, requiring substantial infrastructure and permanent installations. They operated at relatively long wavelengths that couldn't detect small objects or provide precise location information. They were completely unsuitable for installation on aircraft or small vessels. What the Allies desperately needed was radar small enough to fit in an aircraft, powerful enough to detect submarines on the surface, and precise enough to guide attacks in complete darkness. Every technical expert consulted agreed this was impossible with current technology. The wavelengths required for precision detection couldn't be generated with sufficient power. The components needed would be too large and heavy for aircraft installation. The power requirements exceeded what aircraft electrical systems could provide. The cooling requirements for high-power transmitters couldn't be met in confined spaces. The consensus among radar specialists was clear. Airborne submarine detection radar was theoretically possible, but practically unachievable, with 1940 technology. Development efforts should focus on incremental improvements to existing systems rather than pursuing revolutionary capabilities that couldn't be realized. This was the expert opinion that nearly prevented development of the weapon that would win the Battle of the Atlantic. The problem was that Britain was losing the war at sea. German U-boats were sinking merchant ships faster than they could be replaced. In 1942, Allied shipping losses exceeded 6 million tons, with U-boats accounting for the vast majority. Britain's food imports were dropping dangerously. Fuel supplies were critically low. If the losses continued at this rate, Britain would be starved into submission within a year, regardless of how well the RAF defended against German bombers or how bravely the army fought in North Africa. Winston Churchill later wrote that the only thing that truly frightened him during the entire war was the U-boat peril. The statistics justified his fear. At the current loss rate, Britain would run out of merchant ships before Germany ran out of submarines. The mathematics were brutally simple and pointed toward defeat unless something fundamental changed in the Atlantic battle. The U-boat's greatest advantage was their ability to operate on the surface at night. Submerged, a U-boat was nearly blind, slow, and limited by battery capacity. On the surface, it could travel at high speed using diesel engines, spot convoys from miles away, coordinate wolf pack attacks, and dive quickly if threatened. Allied aircraft could only attack submarines they could see, which meant daylight attacks or rare encounters when star shells illuminated targets at night. The vast majority of U-boat operations occurred in darkness that rendered them effectively invisible. If aircraft could detect submarines in complete darkness, the entire tactical situation would reverse. U-boats would be forced to remain submerged, reducing their speed and operational range. They couldn't coordinate wolf-pack attacks while underwater. Their battery limitations would severely restrict their ability to intercept convoys. the advantage would shift dramatically toward the Allies. But this required radar that supposedly couldn't be built. Telling and preparing. This story took us a lot of time, so if you are enjoying it, subscribe to our channel, it means a lot to us. Now, back to the story. Enter the cavity magnetron, a device that would revolutionize not just radar but the entire trajectory of 20th century technology. Developed by British physicists John Randall and Harry Boot at the University of Birmingham in 1940, the cavity magnetron solved the fundamental problem that had made short-wavelength, high-power radar impossible. It generated radio waves at microwave frequencies with power levels thousands of times greater than previous devices, while remaining small enough to fit in an aircraft. The technical breakthrough was elegant in concept, though devilishly difficult to manufacture. The magnetron used a cylindrical metal block with precisely machined cavities that resonated at specific frequencies. Electrons circulating in a strong magnetic field excited these cavities, generating powerful microwave radiation. The device could produce 10 kilowatts of power at wavelengths of 10 centimeters, specifications that radar experts had declared impossible just months earlier. British scientists recognized immediately that the cavity magnetron represented the key to airborne submarine detection radar. But Britain lacked the industrial capacity to mass-produce the complex device, while simultaneously building aircraft, ships, tanks, and all the other equipment needed to fight a global war. The decision was made to share the technology with the United States, hoping American industrial capacity could turn the laboratory breakthrough into operational equipment before U-boats strangled Britain into submission. In September 1940, a British technical mission travelled to the United States, carrying one of the most valuable cargo shipments in history. Inside a metal box was a cavity magnetron and complete specifications for its manufacture. The British were essentially giving away the most significant military technology, development of the war, gambling that American industrial and scientific capacity could transform it into weapons that would save Britain before the gift became moot. The radiation laboratory was established at the Massachusetts Institute of Technology in October 1940, staffed with some of America's brightest physicists and engineers. Their mission was to develop practical radar systems using the cavity magnetron. The laboratory grew from a handful of scientists to over 4,000 personnel by 1945, becoming one of the most productive research organizations in history. They would develop dozens of radar systems for different applications, but none would prove more important than the one initially rejected as inadequate. The ASV Mark II radar, developed for anti-submarine and vessel detection, was the Radiation Laboratory's first attempt at airborne submarine detection. It operated at 1.5-meter wavelength, used conventional technology, and entered service in early 1941. It was better than nothing, but barely. The system could detect submarines on the surface at ranges of 5 to 12 miles under ideal conditions. It provided only crude direction information. It was unreliable in rough seas where wave reflections created false signals. It gave U-boats enough warning time to dive before aircraft arrived. U-boat commanders quickly learned that ASV Mark II-equipped aircraft could be defeated by maintaining vigilant surface lookouts and diving immediately when aircraft were spotted. The radar's limited range meant U-boats had time to submerge if they reacted quickly. By mid-1942, U-boats were escaping most airborne radar contacts by diving before aircraft closed to attack range. The ASV Mark II was failing to deliver the decisive advantage the Allies needed. What was required was a quantum leap in capability, not incremental improvement. Aircraft needed radar that could detect submarines at ranges of 20 to 30 miles, providing enough detection distance that even crash diving. U-boats couldn't escape. The system needed to work reliably in all weather and sea states. It had to be compact and light enough for installation in patrol aircraft without compromising their range or payload. It required sufficient precision to guide attacks in zero visibility conditions. This specification described what became the ASV Mark III radar, later known in American service as the SCR-517 and in the British designation system as the Type 179. Development began in late 1941, using the cavity magnetron as its core technology. Every radar expert who reviewed the specifications declared them unattainable. The detection range requirement alone seemed impossible, given the power limitations of airborne installations. The engineers at the Radiation Laboratory and Britain's Telecommunications Research Establishment proceeded anyway, driven by the knowledge that Britain's survival depended on solving supposedly impossible technical problems. They attacked each limitation systematically, developing solutions that pushed the boundaries of contemporary technology. The cavity magnetron provided the high-power microwave transmission that made long-range detection theoretically possible. But converting theory into functioning hardware required solving dozens of interconnected problems. The magnetron needed to be shock-mounted to survive aircraft vibrations and landing impacts. The waveguide components that channeled microwave energy from the magnetron to the antenna had to be precisely manufactured to minimize power loss. The antenna needed to scan rapidly to search large areas while maintaining enough dwell time on targets to collect adequate return signals. The receiver presented equally daunting challenges. It needed to detect incredibly faint echoes, reflected from small metal objects 30 miles away, while discriminating against vastly stronger reflections from waves, clouds, and land features. The signal processing had to happen in real time, providing continuous updates as the aircraft maneuvered and targets moved. All of this needed to be accomplished with 1,942 vacuum tube electronics before transistors or integrated circuits existed. The display system required innovation that seems obvious in retrospect, but was revolutionary at the time. The Plan Position Indicator, or PPI display, showed radar contacts on a circular screen with the aircraft at the center. Each sweep of the radar beam added new information to the display, building up a map-like picture of surrounding areas. Operators could see multiple contacts simultaneously, track their movements, and guide the aircraft toward targets. This single innovation transformed radar from a simple detection device into a tactical information system. By mid-1942, prototype ASV Mark III systems were undergoing testing. The results exceeded even optimistic predictions. Under favorable conditions, the radar could detect submarine-sized objects at ranges exceeding 30 miles. It worked reliably in weather that would have made visual detection impossible. The PPI display provided clear, interpretable information that operators could master with relatively brief training. The system's size and weight, while substantial, could be accommodated in patrol aircraft like the B-24 Liberator without critically compromising performance. But there was a problem. The U.S. Navy, whose approval was required for American production and deployment, rejected the ASV Mark III as inadequate for operational use. Their objections focused on several concerns. The system was too complex for reliable operation in combat conditions. Maintenance would require specialized technicians and equipment unavailable at forward bases. The radar's range, while impressive, wasn't consistent enough for reliable tactical planning. The precision needed for blind attacks in darkness couldn't be guaranteed. Training operators to use the system effectively would take too long. The Navy's position reflected genuine concerns about deploying complex, untested technology in combat, but it also reflected institutional conservatism and reluctance to disrupt existing procurement and training programs for systems whose performance couldn't be absolutely guaranteed. The official recommendation was to continue with incremental improvements to the ASV Mark II while conducting further research on microwave radar that might eventually produce acceptable performance. This decision would have been disastrous. By the time further research produced systems the Navy considered acceptable, Britain might well have been starved into surrender. The Battle of the Atlantic was being lost in 1942, not in some theoretical future when perfect technology would be available. Fortunately, the Royal Air Force Coastal Command was more willing to gamble on imperfect but revolutionary technology. Air Chief Marshal Sir Philip Joubert, who commanded Coastal Command from June 1941 to February 1943, recognized that the ASV Mark III represented a potential game-changer despite its limitations. His aircraft were flying endless patrols over the Atlantic with inadequate equipment, finding few submarines, and watching convoy losses mount. If the new radar worked even partially as promised, it would dramatically improve their effectiveness. If it didn't, they would be no worse off than they were already. Joubert pushed for immediate operational deployment despite American rejection of the system. British production of ASV Mark III began in late 1942, with initial installations in Wellington and Liberator aircraft of Coastal Command. Operators received intensive training on the new equipment. Maintenance procedures were developed through trial and error. Initial results were mixed as crews learned to use the unfamiliar technology, but gradually the system's potential began to emerge. In March 1943, the tide of the Battle of the Atlantic turned decisively. That month, U-boats sank 108 Allied merchant ships, a catastrophic loss, a rate that suggested Germany was winning the war at sea. But it would be the last German victory. In April, sinkings dropped to 56 ships. In May, they fell to 50 ships, while U-boat losses spiked to 41 submarines destroyed. Admiral Karl Dönitz, commander of the U-boat force, was forced to withdraw submarines from the North Atlantic in late May, conceding defeat in the campaign that had nearly won Germany the war. Multiple factors contributed to this dramatic reversal. Allied convoy tactics improved with better coordination between surface escorts and air support. The Allies closed the mid-Atlantic air gap by deploying very long-range aircraft that could cover areas previously beyond land-based air power. Intelligence breakthroughs allowed Allied forces to route convoys around known U-boat concentrations. But the single most important factor was airborne radar that allowed aircraft to detect and attack submarines with unprecedented effectiveness. The ASV Mark III radar transformed anti-submarine warfare by eliminating the U-boat's sanctuary of darkness. Submarines that previously operated with relative impunity on the surface now faced detection and attack from aircraft they couldn't see or hear until bombs were already falling. U-boats were forced to remain submerged far more often, reducing their operational effectiveness. The psychological impact on U-boat crews was devastating, as they realized nowhere was safe. The statistics tell the story. In the first 4 months of 1943, before ASV Mark III achieved widespread deployment, Coastal Command aircraft sank 6 U-boats. In May 1943, as the new radar reached operational maturity, Coastal Command sank 10 U-boats. By the end of 1943, aircraft equipped with ASV Mark III and its American equivalent had accounted for over 40 U-boat kills. More importantly, the mere threat of radar-equipped aircraft forced U-boats to abandon aggressive surface tactics that had made them so effective. The tactical revolution was profound. Previously, U-boats detected convoys visually from their conning towers, surfaced at night to attack, and coordinated wolf-pack tactics through radio communication while on the surface. ASV Mark III forced them to remain submerged during daylight and surface only briefly at night to recharge batteries and ventilate the boat. This dramatically reduced their ability to locate convoys, coordinate attacks, and intercept targets. U-boat commanders tried various countermeasures. They installed radar warning receivers that could detect the emissions from Allied radar, but these only confirmed they were being hunted without providing effective defense. They experimented with schnorkel devices that allowed submarines to run diesel engines while at periscope depth, but these reduced speed and created distinctive visual signatures. They developed anti-aircraft weapons to fight back against aircraft, but submarines caught on the surface remained vulnerable during the time needed to man defensive weapons. None of these countermeasures succeeded in negating the advantage ASV Mark III provided to Allied aircraft. The radar worked too well, detecting submarines at ranges that gave aircraft overwhelming tactical advantages. By the time U-boat lookouts spotted an approaching aircraft, it was too late to dive to safety. Submarines, caught even partially surfaced, became easy targets for depth charges and rockets. The hunter-killer relationship reversed completely. The American military's initial rejection of ASV Mark III became a source of considerable embarrassment as the system's success became undeniable. By late 1943, U.S. Navy patrol aircraft were being equipped with the SCR-517 variant over the objections of officials who had declared the system inadequate. American submarine hunters achieved results comparable to their British counterparts once they received the equipment that had been rejected as impractical just months earlier. The story of ASV Mark III exemplifies several recurring themes in military innovation. Revolutionary technologies often face rejection from institutions that prefer incremental improvement over risky leaps. Systems dismissed as too complex or unreliable frequently prove decisive when deployed, despite official skepticism. Desperate circumstances sometimes force adoption of technologies that would be rejected during peacetime. The gap between laboratory promise and operational effectiveness can only be bridged through combat experience. The development of ASV Mark III also highlighted the importance of international scientific cooperation. British scientists made the fundamental breakthrough with the cavity magnetron. American industrial capacity mass-produced the devices and integrated them into operational systems. British operational experience demonstrated the system's effectiveness and refined tactics. American resources scaled production to equip the hundreds of aircraft needed to dominate the Atlantic. Neither nation could have achieved victory alone. The cavity magnetron's impact extended far beyond military applications. After the war, microwave technology revolutionized telecommunications, enabling long-distance telephone networks and satellite communications. It made possible modern radar systems for air traffic control and weather prediction. It led directly to the microwave oven, transforming food preparation. The technology dismissed as too complex for practical use became foundational to modern civilization. The engineers and scientists who developed ASV Mark III never received the public recognition given to more visible weapons like bombers, tanks, or battleships. Their work was classified throughout the war and remained obscure afterward. Few people outside specialist circles know the names of those who designed the radar systems that won the Battle of the Atlantic. Yet their contribution to Allied victory was as significant as any weapon deployed during the war. Admiral Dönitz later wrote that the introduction of airborne microwave radar represented the decisive turning point in the Battle of the Atlantic. He acknowledged that once Allied aircraft could detect submarines at extended ranges in any weather or visibility conditions, U-boat operations became untenable. The technology he couldn't counter forced him to abandon the campaign that nearly won Germany the war. His assessment confirms what the statistics demonstrate. ASV Mark III was the weapon that broke the U-boat threat. The story of how one rejected radar set tracked U-boats 30 miles beyond sight teaches important lessons about innovation in crisis. Sometimes the expert consensus is wrong. Sometimes impossible means merely very difficult. Sometimes the gap between laboratory curiosity and war-winning weapon is shorter than anyone expects. Sometimes desperate circumstances force acceptance of imperfect solutions that prove more effective than perfect systems that arrive too late. The ASV Mark III radar, the imperfect innovation that won the Atlantic War, rarely rewards perfection. It rewards what works, what can be fielded, maintained, and trusted under the most brutal and unpredictable conditions imaginable. In the long and bitter struggle of the Battle of the Atlantic, perfection was a luxury the Allies could not afford. What they needed was a weapon that worked well enough, and the air-to-surface vessel, ASV Mark III radar, became precisely that. The ASV Mk3 was not flawless. It had blind spots, mechanical fragility, and calibration problems that frustrated operators and engineers alike. But in the end, it did not need to be flawless. It needed only to be operational at a time when Britain's survival and the Allied war effort depended on restoring control of the Atlantic. It was a victory of pragmatism over perfectionism, a principle that has shaped military technology ever since. By early 1942, the Allies were losing the Battle of the Atlantic. Convoy losses were staggering: over 800 ships sunk in a single year. Each merchantman destroyed meant fewer tanks in Egypt, fewer shells in Russia, and fewer calories in Britain's rationed kitchens. The Royal Navy and Royal Air Force Coastal Command faced a cruel paradox. They had air patrols, ships, and sonar, but their ability to find the enemy, the elusive U-boats, was crippled by night, weather, and vast ocean distances. Most submarines were sunk only by chance. Radar was the obvious answer. The Allies already possessed surface search radar systems, such as the ASV Mark II, which operated at a wavelength of about 1.5 meters. But this early radar could only detect a surfaced submarine at short range and only in good weather. Worse, the Germans had countered it with their Metox radar detector, which warned U-boat crews whenever Allied aircraft were searching nearby. It became a deadly game of cat and mouse. The moment the Metox receiver squealed, the submarine dove beneath the surface and disappeared. Allied pilots often arrived at an empty patch of sea. If the Allies could not overcome this problem, Britain might starve before D-Day ever became possible. Enter the cavity magnetron, one of the most important scientific breakthroughs of the 20th century. Developed by British physicists John Randall and Harry Boot in 1940, it generated powerful microwaves at centimetre wavelengths, a feat previously thought impossible. These shorter wavelengths promised unprecedented resolution. Radar beams could now focus tightly enough to detect small targets, even a periscope tip slicing through the sea. The concept was revolutionary, but initially dismissed as impractical. Critics within the Air Ministry argued that the technology was too fragile, that the shorter wavelengths would scatter in rain or fog, and that production would take years. In the middle of a war, they insisted, it was better to refine existing systems than gamble on unproven theory. But events would soon silence them. Britain's shipping losses were climbing faster than new ships could be built. Each convoy that failed to reach port represented another nail in Britain's coffin. By late 1941, desperation forced decision-makers to reconsider every assumption. When the magnetron's potential was demonstrated to radar officers detecting a submarine's periscope from miles away, at night the reaction was immediate. It wasn't just a new tool, it was a potential miracle. The challenge was transforming that laboratory miracle into a rugged, battlefield-ready radar. Engineers at the Telecommunications Research Establishment, TRE, and their American counterparts worked feverishly to miniaturize the magnetron and integrate it into aircraft systems. The result, achieved by late 1942, was the ASV Mark III radar, the first practical centimetric radar designed for maritime patrol aircraft. It was far from perfect. It was expensive and difficult to produce. It required frequent calibration to maintain accuracy. It sometimes generated ghost echoes in heavy seas. And it was blind directly below the aircraft, forcing pilots to coordinate precisely with radar operators during attack runs. But despite its flaws, the ASV Mark III represented a quantum leap in capability. It could detect a submarine's conning tower at ranges of 7 to 10 miles, and sometimes farther. It could penetrate darkness, fog, and cloud cover. And unlike its predecessors, it was completely undetectable by the Germans' Metox receivers. This last feature alone changed everything. The once predictable advantage of surfacing under cover of darkness vanished. Allied aircraft could now attack without warning, often before the U-boat even realized it had been spotted. The first aircraft to carry the ASV Mark III radar was the Ley light-equipped Wellington bomber. This combination proved deadly. The radar would guide the aircraft to within a mile of its target. Then at the last moment, the Ley light, a powerful searchlight mounted beneath the fuselage, would illuminate the submarine, blinding its crew just seconds before bombs or depth charges struck. For U-boat sailors, it felt supernatural. They could no longer rely on darkness or poor weather to protect them. The first inkling of danger often came when the ocean around them suddenly erupted in white light and explosions. As the radar spread to long-range patrol aircraft, particularly the American-built consolidated B-24 Liberators and PBY Catalinas, the effect was transformative. The B-24's massive range allowed continuous patrols deep into the mid-Atlantic, a zone previously out of reach for land-based aircraft. By early 1943, the infamous Black Gap, where convoys were once defenseless, had been closed. The results were immediate and devastating for the Germans. In March 1943, Dönitz's U-boat fleet suffered its worst losses of the war, 41 submarines sunk in a single month. The Hunter had become the hunted. Despite its revolutionary performance, the ASV MK3 was never a flawless piece of engineering. Operators complained about its bulk, sensitivity to vibration, and difficulty interpreting its displays in turbulent flight. But it met the one criterion that mattered most. It was operationally reliable. It could be maintained at forward bases by mechanics with limited training. Replacement parts could be scavenged or repaired in the field. And its interface built around the new Plan Position Indicator, PPI, display was intuitive enough for radar operators to learn quickly. This new circular screen, showing the aircraft at the center with radar returns sweeping outward like a clock hand, became an instant revolution in situational awareness. Pilots could now see their own position relative to the target, the coastline, and other aircraft a leap forward from the crude, oscilloscope-style displays of earlier systems. That simplicity and usability, more than technical perfection, made the ASV MK3 a battlefield success. As one Coastal Command officer later remarked, "It worked when we needed it. That's what mattered. We could train crews fast, keep it running, and bring our boys home alive." The impact of ASV MK3 extended far beyond the sinking of U-boats. It reshaped the philosophy of military innovation. Speed over perfection. The radar was deployed even while engineers were still refining it. The lesson was clear. An imperfect weapon in combat is worth more than a perfect one in a laboratory. This principle would later guide Allied projects like the Proximity Fuse and Jet Propulsion programs. Cross-national collaboration. The radar's success was inseparable from Allied cooperation. Britain's magnetron invention, shared with the United States through the 1940 Tizard mission, enabled American industry to mass-produce the technology at scale. American engineers integrated it into aircraft. British crews perfected its use in combat. The result was a true partnership of science and strategy. Operator-centered design. The PPI display was a quiet revolution. Instead of demanding that users interpret abstract data, it presented information in a visual, intuitive format. This approach, designing systems for human comprehension, first became a cornerstone of all modern radar, sonar, and air traffic control systems. Doctrine transformation. The radar didn't just give the Allies better eyes, it changed how they fought. Air patrols shifted from random sweeps to radar-guided interception. Escort groups coordinated attacks based on shared radar data. The Atlantic, once an ocean of uncertainty, became an increasingly mapped and monitored battle space. Technological breakthroughs alone never win wars. It was the air crews, the radar operators hunched in dark, freezing compartments, who turned the ASV MK3 into a war-winning tool. Radar training schools sprang up across Britain, turning out thousands of operators in just weeks. Many were barely out of their teens. They learned to read faint echoes and distinguish a submarine's periscope from a wave crest. They learned patience, long hours of staring into the green glow of a cathode ray tube, waiting for a blip that might mean life or death. The teamwork between pilot and radar operator was critical. Communication had to be wordless, instinctive. When a contact appeared, the operator's calm voice guided the pilot through turns and altitude changes until the target came into view. Then, at the operator's final countdown, the lee light blazed on and the bombs fell. To those crews, the radar wasn't just equipment. It was a lifeline, a silent companion in the endless dark. By mid-1943, the transformation was complete. The U-boat threat that had once seemed unstoppable was in retreat. The Allies' technological advantage, radar, sonar, direction finding, and improved weapons had converged into an overwhelming superiority. Convoy losses plummeted. In May 1943 alone, the Allies destroyed 43 U-boats while losing only a handful of ships. Admiral Karl Dönitz, commander of the German submarine fleet, recalled the moment bitterly. "We were no longer the hunters, we were prey." The strategic consequences were immense. The secure Atlantic lifeline allowed the United States to build up its armies in Britain, paving the way for the Normandy invasion in 1944. Without radar dominance, D-Day might have been impossible. The legacy of the ASV Mark III radar extends into every modern radar system used today, military, civilian, and scientific. The cavity magnetron remains the beating heart of microwave technology, found not only in radars but even in the humble kitchen microwave oven. The PPI display became the universal standard for radar screens, from air traffic control towers to ship bridges. But perhaps the most enduring legacy lies in the philosophy it embodied, the courage to deploy innovation before it was perfect. Modern defense research programs, from stealth aircraft to cyber systems, still draw upon this lesson. Good enough is not mediocrity, it is the discipline of recognizing when a technology's potential outweighs its flaws, and when waiting for perfection could mean strategic disaster. The principles forged in the radar labs of 1942 continue to shape 21st century innovation. Rapid prototyping. The same agile, iterative development used for ASV Mark III now defines modern technology programs. Joint innovation. The British-American partnership of the radar project foreshadowed NATO's integrated defense research and multinational programs like the F-35 fighter. Dual-use technology. The magnetron bridged war and peace, a military device that found peaceful applications in medicine, communications, and consumer electronics. In every airport radar, weather tracking satellite, and maritime surveillance system, a trace of the ASV Mark III's DNA remains. In the end, the U-boat that could no longer hide gave birth to the radar that could not fail. The Battle of the Atlantic, once a desperate struggle for survival, became a proving ground for a new kind of warfare, one defined not by brute force, but by information dominance. The Atlantic, once a graveyard for convoys, became an allied lake. The ASV Mark III radar didn't win because it was perfect. It won because it was possible. It was a triumph of applied science under pressure, a symbol of human ingenuity, finding light in darkness, both literal and metaphorical. And as aircraft today scan oceans, skies, and even distant planets with radar pulses that owe their existence to that wartime innovation, the story of the ASV Mark III endures as a reminder that sometimes good enough is what saves civilization. Up next, we have two more incredible stories that are waiting for you. Just click the image you want to watch, and it will take you there. If you enjoyed this video, make sure to subscribe, it would mean a lot.